Welcome to Sift Tutorials. We ended our last tutorial having created a residual power signal. This was calculated as the difference between measured power and an expected power calculated using historic operational data. In this video, we will set up an analysis with these power residuals to monitor turbine power curve efficiency over time. Let's create a KPI. In Sift, KPIs are a very flexible way to roll up data and visualize trends and deviations. A few useful KPIs have been pre-configured. You can read about these in the user guide. For our KPI to monitor turbine performance, we will create a custom KPI. We can rename the KPI to something more recognizable here. In this analysis, we will compute turbine power curve efficiency in normal uncurtailed operation over time. We will create separate metrics of turbine efficiency at full load, where we expect rated power, and partial load, where the turbine is producing power but does not reach rated. Having two targeted metrics for the different parts of the power curve makes the output easier to interpret. Let's focus on partial load operation first. Power curve efficiency in partial load can be calculated by dividing the sum of observed power by the sum of expected power. Note that having summed 10-minute power in kilowatts, we can convert our values to production in kilowatt hour by then dividing 6, as there are 6 10-minute samples in an hour. In the efficiency calculation, these factors in the numerator and denominator would cancel out. This is equivalent to 1 minus the total losses divided by the total expected production. The loss over expected power computes the efficiency deviation from expected. We will therefore start by calculating the sum of power residual in partial load. The limitation to partial load is done by adding a filter string, which is set to neutral data, where generator speed is above cut-in and power is below 95% of rated power. We set the minimum sample count to 12 to ensure we have enough data to create an accurate estimate of efficiency. We can do the same for the expected power signal. Note the filter string should be the same as before. Power curve efficiency can then be calculated using a KPI expression. KPI expressions allow us to create a new KPI based on KPIs above. The final expression is this. Let's now move on to full load. The calculation is set up the same as before, except for the filter strings, which select which part of the power curve is included in the analysis. We limit our data to high power and high pitch. High pitch is used to exclude transitional points near the knee of the power curve. For this analysis, we are not interested in the entire history of the turbine, so we do not need to work around pitch data coverage issues we've seen in previous tutorials. We want the output to only include our efficiency values, so let's deselect the other ones. To analyze each turbine separately and get separate estimates by month, we set grouping dimensions to instance and year and month. Note that these are the default values here. We select all the turbines in the instance selector and press calculate. Let's have a look by pressing visualize. The default view for KPIs is a heat map, which is now showing the partial load power curve efficiency as indicated here. We can get a line plot in the bottom panel by selecting rows or columns in the top panel. Simply click the top one and drag the selection down. We can see a clear seasonal component in our partial load power curve efficiency that repeats every year. At the end of the dataset, there are also two turbines with large drops in efficiency. The binned map approach we have used to calculate expected power could be improved to reduce this seasonality. The drops in efficiency at the end of the dataset highlight an issue that we would normally investigate further. Let's look at the power curve efficiency in full load. In the full load KPI, there are some gaps due to high wind speeds being less frequent. Most deviations are within 1%. There are many possible reasons for the observed deviations in power curve efficiency. These include changes in turbine control, imperfect data cleaning, and measurement issues, often changes to the turbine anemometry. In this series, we have shown the building blocks of setting up an analysis on operational wind turbine data. We hope you feel empowered to use these in setting up your own analysis.